Hello and welcome. The main objective of this lesson is that to make the learners to understand what is Joule Thomson effect and Joule Thomson coefficient. Then we will discuss about throttling of ideal gas and real gas and the variation of temperature change with the pressure change. Then we will discuss about throttling of real gas at different isenthalpic conditions for various gases. Like gases we will take like air and hydrogen. Then we will see the nature of Joule Thomson coefficient. Means we will see what is heating region and what is cooling region. And in the last we will also see what is the application of Joule Thomson coefficient and how it is useful for refrigeration systems. Thank you. We are moving towards the video lecture. Welcome. Today we will see what is Joule Thomson effect and Joule Thomson coefficient. First we will see what is Joule Thomson effect. Joule Thomson effect is the temperature change of any fluid. Here we are taking the fluid as real gas. The temperature change of real gas occurs because the gas is passed through the restricted medium. Restricted medium can be like wall, or it can be porous medium like porous plug. Due to restriction in the flow of the passage of the real gas, there is the case that pressure will drop in the downstream. So we can say the real gas is flowing from high pressure to low pressure region and without any heat transfer. Summing the definition, Joule Thomson effect means temperature change of a real gas when it is passed through the restricted passage from high pressure to low pressure region without any heat transfer. So, dear, recall the definition of throttling process. Throttling process also means the same. It is the restriction in the path of the flow. To understand throttling process in a better way, this is a diagram I have made. This is the throttle valve which is moving up and down to restrict the flow. This is the pipe in which fluid is moving, like real gas is moving. This is the inlet conditions P1, this is the exit condition P2, as the fluid is flowing from high pressure region to low pressure region. So P1 pressure is greater than P2, so fluid is moving from left hand side to the right hand side. Now coming to some points regarding throttling process, recalling the characteristic of throttling. In throttling process, fluid always move from high pressure region to low pressure region because of the restriction in the path. So we can say throttling process is an irreversible process. It can never be reversible because it cannot flow from low pressure region to high pressure region. And the other thing with the throttling process is that it is an isenthalpic process. Isenthalpic means that the inlet enthalpy is equal to exit enthalpy. It means energy is conserved during the process. So by seeing the above condition, that is H1 is equal to St, H1 is equal to H2, we can conclude there is no energy loss or energy gain or energy transformation during the process. The above condition, that is H1 is equal to H2, that is isenthalpic condition, we can also prove it by steady flow energy equation, SFEE. This is the equation of first law of thermodynamics for open system. Throttling process can be seen in any fluid. So here we are taking two fluids. First is ideal gas, second is real gas. And we analysis more in that. Coming to the diagram at the inlet condition, that is pressure is P1 and temperature is T1. Coming to the exit condition, pressure is P2 and temperature is T2. Due to restriction, this temperature can increase, can decrease, or can remain constant. Now coming to the ideal gas. In ideal gas, we know that enthalpy is the function of temperature only. And in throttling, enthalpy is constant. Therefore, we can say temperature is also constant. That is T1 is equal to T2. Now coming to the real gas. In real gas, enthalpy is not the function of temperature only. It is the function of other variables also, like pressure and volume. And here in throttling, H1 is equal to H2. But we cannot say that temperature is also equal during the process, because enthalpy is not the function of temperature only. It is the function of other parameters also. So therefore, in real gas, exit temperature can increase, decrease, or can remain constant. To understand the nature of the temperature, Joule Thomson conducted an experiment for the real gas and plotted the results on the PT diagram. To check whether the temperature will increase, decrease, or remains constant during the process. So, moving ahead, I am plotting the pressure and temperature diagram. Pressure on x-axis, temperature on y-axis. The process will occur from right hand side to left hand side in the diagram. After plotting, we found a line, a curve in the PT diagram. This curve is known as isenthalpic line, because the throttling process is happening at constant enthalpy. Yes, we will move from right hand side to left hand side in the diagram. Pressure is decreasing in this direction. In the above diagram, we will move from left hand side to the right hand side, since pressure is decreasing in that direction. Moving ahead in the throttling process, the Joule Thomson coefficient is represented. The Joule Thomson coefficient is represented by the symbol mu, and mu is equal to dt by dp at constant enthalpy. In any diagram, like in xy diagram, we know that dy by dx is equal to slope. So by seeing this diagram, dt by dp is equal to dv by dx is equal to slope is equal to mu, means Joule Thomson coefficient. Mu is representing as a slope, which is equal to dt by dp. And we also know that this line in the diagram representing as a positive slope, and this line in the diagram representing as a negative slope, and this horizontal straight line representing as a zero slope. Like we can see this situation in the ideal gas. How? like for ideal gas. Because here T1 is equal to T2, we will plot this temperature in the TP diagram. This is the pressure reducing in this direction. One process is happening T1 to T2. We will see temperature is constant. So here mu is equal to 0, slope is equal to 0. So we can say the Joule Thomson coefficient for ideal gas is equal to 0. Now coming to this diagram for which we are analyzing, this is the throttling process for the real gas. Now indicating some points on this isenthalpic line to show the behavior of the slope, that is mu. Drawing a tangent at the point B, I am seeing that the slope is 0, so I am writing mu is equal to 0. Separating different sections like AB and CB and analyzing slope for these regions. Like for AB region, the slope comes out to be negative. I have shown earlier. Therefore, mu is equal to negative. For this section BC, the slope is positive. Therefore, the Joule Thomson coefficient mu is positive. We are moving ahead with these two sections and analyze what will be their results of temperature. In the first section, that is A to B, mu is negative. I have written, and with the formula says mu is dt by dP at constant enthalpy. Since mu is negative here in the AB section, so we can write dt and dP as we can write dt as TB minus TA final minus initial, and dP as PB minus P final minus initial. In throttling, we are moving from high pressure region to low pressure region, so pressure PB is less than pressure P. Therefore, the PB minus PA comes out to be negative. And here, to make the Joule Thomson negative, TB minus TA should be positive. Therefore, by this, mu will remain negative for section AB. To make the above equation positive, TB should be greater than TA. So, by seeing this, we can conclude that temperature increases during negative Joule Thomson coefficient, that is in the section AB. Moving to the next section, that is from B to C. Here we know that Joule Thomson coefficient is positive and mu can be written as dt by dP. Positive. Tt can be written as Tc minus Tb, and Tp can be written as Pc minus Pb, final minus initial. And we know that Pb is greater than Pc. So therefore, we can conclude Pc minus Pb is negative. To make the Joule Thomson coefficient positive, Tc minus Tb should also be negative, and this can only occurs when Tc should be less than above equations come out to be negative. Therefore, we can conclude temperature decreases during positive Joule Thomson coefficient. Seeing the temperature behavior in the Peting diagram, we notice that in the AB diagram temperature is increasing. So we can write T is increasing and we can say it is a heating region. And in the BC region temperature is decreasing, so we can say that it is a cooling region. Summing the definition, we can say that in the AB section where the Joule Thomson coefficient is negative, gas is showing the heating effect after throttling. And where the Joule Thomson coefficient is positive, gas is showing the cooling effect after throttling. We found a point in the diagram, PT diagram, where the nature is changing, where the mu is 0. It is the inversion temperature point, where the Joule Thomson coefficient is 0. Seeing the cooling effect and heating effect, therefore Joule Thomson coefficient mu is very much useful in HVAC systems, heating, ventilation, air conditioning systems. Plotting the result of the real gas for different enthalpy condition, we found this type of diagram, PT diagram, joining the locus point of the inversion temperature. We find this type of curve. In the right hand side of the curve, as temperature is increasing, we also know that Joule Thomson coefficient is negative, so we can write mu is less than 0, and at the left hand side mu is greater than 0, as Joule Thomson coefficient is positive in left region. This is the inversion line because it is made from inversion temperature. These are different enthalpy conditions, H1, like H1, H2, H3 and H4. These are constant enthalpy lines. We are doing throttling at different enthalpy conditions. This intersection point of temperature and inversion line is called as maximum inversion temperature. This is the important temperature in Joule Thomson coefficient concept. These are H1, H2, H3, H4. We noticed in the diagram that above maximum inversion temperature, there is only heating effect we are getting after throttling of any gas. This is a thumb rule. Above maximum inversion temperature, we will only get the heating effect of the gas. So examine more with this inversion temperature, maximum inversion temperature. We analyze maximum inversion temperature for different gases and move forward and plot this maximum inversion temperature in the diagram. I am taking some gases. These are approximated values. Like helium, its maximum inversion temperature is minus 230 degrees centigrade. For hydrogen, it is minus 71 degrees centigrade. For neon, this maximum inversion temperature is minus 13 degrees centigrade. For air, this temperature is 330 degrees centigrade. For nitrogen, it is 350 degrees centigrade. Oxygen, it is 488 degrees centigrade. These are approximated values. Plotting the temperature of maximum inversion temperature for air. In the diagram we are plotting. Maximum inversion temperature is 330 degrees centigrade, and below we are plotting some temperatures. Roughly we are plotting some temperatures value. After plotting this maximum inversion temperature and other temperature on PT diagram for air, we find that below maximum inversion temperature, both heating and cooling regions, or both heating and cooling effect is obtained from the gas. But if a gas is throttled up to 330 degrees centigrade, we will only find heating effect from the gas. Above 330 degrees centigrade, it will show only heating effect. Again, plotting this maximum inversion temperature for hydrogen and coming to the results, like maximum inversion temperature for hydrogen is minus 71 degrees centigrade. Minus 71 degrees centigrade. For example, this temperature is ambient temperature, that is 27 degrees centigrade, and temperature is decreasing in downward direction. So roughly I have plotted. So here we have noticed that if the hydrogen gas is throttled up to ambient condition, it will only show us heating effect, because the maximum inversion temperature of hydrogen, helium or neon is less than the ambient conditions. If we want to use the hydrogen for refrigeration system, first we have to cool the hydrogen gas up to maximum inversion temperature with the help of nitrogen gas, and then we will proceed for